All right, thanks for that. Thanks for tuning in. So as Sergi mentioned, my name's Lester. I work at Verizon Media Group, previously Yahoo, and as Sergi also mentioned, we're soon to be called Yahoo yet again. I primarily work on machine learning solutions, and today I'll be talking about nearest neighbor search. Specifically, some practical issues to think about when using ANNs in search applications. Because there's been a lot of buzz around the nearest neighbors in recent years. We've seen a lot of libraries and platforms appear, but not too much talk about some of the more practical problems that need to be solved. And I'll try to exemplify them using some real applications. So as Sergi mentioned, at Verizon I work on the Vespa platform. And if you're not familiar with it, Vespa is the open source platform for low latency computations over large evolving data. It's a platform we've been developing over many years. It has roots spanning back to the search engine wars of the late 1990s. But we open sourced it a few years back, so while it may seem new to many people, it's been battle tested over many years, and today serves hundreds of thousands of queries per second at any given time all over the world, serving hundreds of applications, hundreds of millions of users each month, and so on. There's a debate, I think, on Thursday, which compares Vespa to Elasticsearch and Lucene, which will surely be great. So check that one out if you're interested in Vespa. So Vespa is fairly feature-rich for many types of applications, and its features are all included and tightly integrated with each other, such as advanced relevance scoring with tensors, machine learning models. One of the really cool features of Vespa is the ability to string together or pipeline various machine learning models from various platforms together across different phases to calculate relevance scores and so on for queries. But that's another talk. For this talk, we'll be looking at nearest neighbors. So with nearest neighbors, we need to start with representations. So pretty much anything can be represented by a list of numbers, or more formally, a point or a vector in high dimension space. Text, images. This is an image of my dog. I was not really sure what's going on. He doesn't like his nearest neighbors. They're mostly cats. But even things like based on time, such as sound or video, or even user interactions, that can be represented by such representations. So I'm not really going to talk about how we generate these representations. Representation learning is a talk of its own, but it's had great progress recently with deep learning. There's, however, one thing I'd like to say, and that we've seen great results when using representations that are trained or adapted specifically for the use case. But these representations don't necessarily work all that well when transferred out of the domain. So for instance, for text, we haven't seen great results when using things like universal sentence encoders in relation to more classical approaches such as BM25 for certain cases. So, but again, I'm digressing. That's another talk. But anyway, these representations that we generate in some way, they map objects into some high dimensional space. This allows us to find or search for nearest neighbors, for instance, to some query points. The nearest neighbors are measured by some distance functions such as geometric distance or Euclidean distance. We have cosine angles, which work well for sparse representations of particular texts, Manhattan distance, Hamming distance when working on bit vectors, and so on. To actually find the nearest neighbors, what we can do is just scan through all points in a kind of brute force manner and determine the closest ones according to some distance measure. Of course, this brute force doesn't really scale that well, so we need some sort of index structure to help us navigate this space. Unfortunately, there aren't really any known methods of doing this exactly, so we need to resort to approximate solutions, which hopefully gives us good enough results. There are a few different methods for this, and I basically divide them into whether or not they can be represented with traditional inverse indexes. Those that can, such as k-means or product quantization and its relatives, locality-sensitive hashing, basically create groups of centroids or buckets for similar items, and you can kind of find the most similar bucket or centroid to the query and prune away a lot of the search space, that way. The other group of methods is those that don't use these inverse indexes, such as hierarchical navigable small worlds, or HNSW, which I'll get back to a little bit later. But basically, this is a graph structure that we search through instead. But for most cases, this is a little bit too low level. Instead, we use libraries to help us do this. And a great resource for that is ANNbenchmarks.com. This site compares various libraries across many different data sets that have different distance measures and vector lengths and so on. And they're graphically compared in figures such as this, which compares recall to queries per second. So up and to the right is better, giving higher recall with higher QPS. Just kind of short word on the measurements here. These graphs are all single CPU, single threads. So they measure the latency and don't really measure the potential for throughput or maximizing the queries per second using, for instance, multiple threads, which is just as, or maybe even more important for many types of applications. So when choosing a library, this is something you might want to think about. At least it's something we care a lot about at Vespa. Anyways, here I've shown just a few libraries to declutter a little bit. Notable ones are Scan from Google, Fies from Facebook, and Noi from Spotify, and of course Vespa. So we have a pull request into ANN benchmarks to include Vespa's ANN implementation, even though it's not really available as a standalone library. But we wanted to measure how good our implementation is against the others. And as you might see, it's not right at the top, but it's competitive with others we compare ourselves to, which is, if you kind of are able to see that, are other libraries that use this HNSW approach. And the reason for that is that Vespa's implementation is, of course, based on the HNSW for a few good reasons. One is, of course, it performs well during retrieval, but perhaps more importantly is that it allows for incremental modification. Now, most of the other approaches I mentioned, they build indexes offline, in batches. So the index is kind of immutable and requires some, or sometimes lengthy indexing periods, particularly for large data sets. But a central design of Vespa is that data that's indexed should be, immediately available for searching. And for many types of application, that's really important. And it's directly supported by the ANNSW algorithm. Now, we've done some modifications to this algorithm, such as allowing removes as well, which is equally important, removing stale data. So in the previous slide, we saw some libraries that do vector similarity search. There are also higher level platforms, such as perhaps Milvus, Weaviate, Pinecone, and so on, that offers a vector search service that you can call out to from your serving stack. Which library or platform you ultimately choose, of course, depends on what type of system you're developing. I mean, background index building might be a perfectly acceptable solution for applications where data doesn't really change that often. However, when it comes to search and recommendation applications, there is another important aspect which isn't touched upon that often, and that is filtering on metadata. So what I mean by that is that most often in a search application, each item in the data usually has associated data with it, or side information or metadata. Now, this metadata is usually stored separately from the library or service implementing the nearest neighbor search, and this can become problematic, as we'll see shortly. So the first example is a semantic search for text. Now, again, assume you have some way of encoding text such that documents or paragraphs or sentences, you can encode them to vectors. One common way these days is to use transformer models such as BERT and so on to and use one of the token vector representations there as an embedding vector. Any way you do this, you can visualize these points in some high dimensional space. Now, assume also that you have some way of encoding a query so that it maps into the same space, so that the closest documents in this space is the most relevant to the query. Now, queries usually have some different properties than documents. For one, they're typically much shorter. So they typically don't use the same encoding model, but to ensure that they kind of map into the same space, one can use like a two-tower configuration, which includes a distance function, and propagate the tuning process. But anyway, mapping the query into the same space, we can find, well, here, for instance, the 10 most relevant documents to the query. And this works well. However, search applications might allow the user to kind of drill into the results by, for instance, here, filtering on the publication year of the document. Now, since we've first retrieved the top 10 documents using nearest neighbor search, and then we filter for the year 2021, we only actually here retrieve the 3 relevant documents to the query. I mean, the other documents, the one in orange here, that are in this space are not recall at all, even though they are relevant to the user. Now, this is kind of a constructed example, but clearly shows the problem we need to solve. So again, to repeat that, I mean, the nearest neighbor search returns the 10 closest items to the query, and applying the filter 2021, 7 out of those 10 results are filtered away, leaving only the 3 that actually pass the filter, which is the ultimate result of this search. So naively, to return the top 10 documents that actually do pass the filter, we need to search in this case for something around 50 results instead of 10. Problem is we don't really know how much to search for beforehand. But we'll see later how we can improve upon this. Another example, recommendation. So recommendation is similar to search, but the query is the actual user profile. We want to search for items to recommend, given what we know about a user. So classically, we'd use approaches such as matrix factorization. These days, of course, use more deep learning approaches, such as neural collaborative filtering and its descendants. These figures here, by the way, they're from a news recommendation tutorial we have for Vespa, in case you're interested. In any case, we create these user embeddings and item embeddings and find the items to recommend by doing a dot product or inner product search between the user embeddings and the item embeddings. This is called maximum inner product search, and it isn't really directly implementable in approximate nearest neighbor algorithms. So we need to convert the MIPS problem to, for instance, a Euclidean distance problem, which allows us to do so. Now, for recommendation services such as YouTube and TikTok and so on, there are a lot of inherent filters we need to consider, such as age appropriateness, banned content, region availability, language, and so on. And there might be more dynamic filters, such as business rules for diversity and deduplication and so on. But all these kind of serve to potentially filter away a lot of otherwise relevant items, so that the effect is that we recall far fewer items than what we otherwise could have. Ad search, another example, similar application really. The image here to the right here is taken from the front page of yahoo.com, which to a large degree runs on Vespa, and you have this kind of infinite scrolling stream. News stream, which has these kind of native ads kind of hidden in the stream. Likewise, users have profiles, as do ads, and the dot product between these two correspond to the kind of interestingness of the ad to the user, at least hopefully. Now these ads also have a lot of metadata, such as target group, target location, geographic location, and so on and so on. But one very important piece of data is the ads or ad campaigns budget. So the advertiser might pay for each impression, and we don't earn any money if we show an ad that has spent budget. So likewise, if we first do a vector search and then perform filters afterwards, there's a real possibility that we aren't really retrieving the most interesting or most profitable ads to show to the user. So In online dating, you have your profile of interests. Now, that's what you are interested in. It could be like pets and travel and food and TV shows, working out, etc., etc. Now, this is your representation. When searching for potential matches, you also have a set of preferences or filters, such as geographical location. You might want to meet people close to you, gender, age range. Are they at least 6 feet tall? And other filters, particularly for services such as Tinder, where you filter away users where you already swipe them left or right. So again, if first retrieving profiles using nearest neighbors, there's a big chance that the people that best match your interests don't pass all of these filters. So many potential matches are not retrieved, and no date for you. Shopping, another obvious example, really. This example here is from a use case in our documentation for using a Vespa in shopping. The use case sample up here even comes with a front end, as can be seen here. Now, products can have their representations, and queries can be mapped to the same vector space as the products. And products have a lot of metadata, of course, the price, category, brands, even rating. Probably one of the important ones is whether or not the item is in stock. Getting results for items that can't be purchased because they're out of stock might be a poor user experience. And again, by first retrieving products using nearest neighbors and then filtering using metadata would likely lead to a lot of relevant products not being retrieved. Finally, local business search. Let's say I want to search for restaurants near me, and we've implemented some sort of personalized search so that my preference profile is used to retrieve the restaurants that best fit my profile. Now, assume that my profile retrieves only the best restaurants in the world. Of course, it's unlikely that they're close to me, at least for the small town that I live up north, which is the red dot up the top there. Well, that's not true. We do have some great restaurants here. We do have a few Michelin stars here. But anyway, restaurants that best fit my profile globally are pretty unlikely to be close to me, meaning that you would very likely not return any results at all. So this is kind of an extreme example. Obviously, you wouldn't do this, but the point stands. So the point being is that post filtering of metadata doesn't really work all that well. So what can you do about that? One obvious approach is to recall more. Just return more items from the nearest neighbor search. However, that can become quite expensive, both in processing and time, especially if these need to kind of cross the network. And still, this isn't really guaranteed to work. Another option is to set up multiple indexes with one per filter. For instance, in a text search example, one index per publication year. Now, this might work if you have a small number of filters and can avoid the explosion of combinations, but still, this adds a lot of complexity. Now, the solution really is to do a nearest neighbor search only among the items that have survived filtering, that is pre-filtering. And the approaches that I mentioned previously, the libraries and platforms, they don't really support this, as the nearest neighbor index and metadata usually are in separate systems. However, in Vespa, we've modified the basic HNSW to support this by introducing eligibility lists. This causes the algorithm to effectively skip items that are not in this list. So in this figure, again, the orange are the items that pass the filter, the blue are items that we want to skip. So the algorithm effectively dynamically increases the search area according to the number of items that we want to retrieve and the items in the eligibility list. And this is nice because we only return the exact number of results that we want to, thus solving the problem of post-filtering. There's perhaps one thing that should be mentioned, and that there's still a slight cost to navigate the graph for items that are skipped. So if the filter is strong, meaning that there are relatively few items in this eligibility list, the cost of searching the graph can be high. And to solve this problem, Vespa falls back to exact nearest neighbor scan, only through the list of eligible items when this happens, because that is actually more efficient than navigating the graph. So, and this threshold is, of course, configurable, and that's one of the kind of nice things that Vespa adds to the table. So to kind of sum up, Vespa innovates a little bit with Approximate nearest neighbors search to fit in with many of the different aspects that are important in search applications. One is the dynamic modification of the graph by particularly supporting removing of items. Uses efficient data structures and methods to increase the performance when building indexes. And it modifies HNSW to support pre-filtering. Now, the implementation we chose to support ANNs are really a consequence of fitting in with the design philosophy of Vespa. And it's important to note that Vespa is much more than a vector search engine. And all the examples that we saw previously are actual applications using Vespa. So some other use cases here, text search using both classic information retrieval techniques such as BM25 and more modern approaches such as vector similarity and transformers such as BERT, etc. Recommendation and personalization using, again, vector search and machine learned models, true partial updates, and so on. Another example which you have a pretty good sample app for is question answering, which uses ANNs to select passages with answers to questions and uses BERT models to extract the exact answer to the question. And we have many more examples, but even finding love. OkCupid, the inspiration for the online dating example, has a great blog post on why they chose Vespa over Elasticsearch. So that pretty much sums up my talk. If you want to know more about Vespa, check out these resources. We have an open source version and a cloud offering as well, which currently has a free trial if you want to check this out. Other than that, tune into the search engine debate on Thursday to learn more. So with that, thanks. And I would open the questions.
Thank you for the great talk. And what is the way to finish it up with finding the love also with Vespa, right?
Yeah, exactly.
Very nice. So we got a few questions from the audience. So first question would be, how customizable is Vespa? Can we develop and plug custom relevance algorithm? I think you mentioned a bit of like custom models, right? But how actually complicated is that to develop a new similarity model or like new algorithm, right? And swap in.
It's very customizable. So basically, Vespa is divided a little bit in two. We call it the kind of stateless front end, and we have a kind of a stateful back end, which where you have all the content and all the that's where all the computation is done. So on the back end, you can write your custom ranking functions to do pretty much whatever computation you want to do using tensors and combining them with machine learning models and so on. In the front end, the stateless layer, you can add your custom Java code, which pretty much can do any form of processing, both when handling queries or ingesting data and so on. So I would say Vespa is very customizable.
Nice, very good. And kind of like a similar question, but from other direction, does Vespa also support traditional relevance algorithm, for example, BM25 TF-IDFs? If yes, how does it work, right? Can you combine them, right? Or you need to decide like it's either one or another one?
No, as I mentioned in just a few slides ago, BM25, or at least these traditional information retrieval techniques, they're very well supported. That's the kind of basis really of Vespa. And they're supported both in forms of matching and the first phase, searching for all documents and using them in ranking as well. So Vespa is very flexible in how you actually match these documents or rank upon them as well. So yeah, these are definitely supported. But one of the nice things is that you can kind of combine these more traditional information retrieval approaches with more modern information retrievals as well, and adding machine learned models to like a later phase models or later phase expression or calculation as well. So yes, Vespa is very flexible in that regard.
So essentially you can get like, top whatever n, right, from a neighborhood, right? And after sort by whatever your like TF-IDF that you were actually aiming for, right? As example, right?
Yeah, exactly. True.
Okay, should be possible. Nice. And what else I have here with questions? There's like more questions popping up. That's why like, okay. So first question, or like third one actually, what are the core features of Lucene that are not supported by Vespa? I guess like people will be like, hey, this is like so amazing. So why do I still need to have Lucene?
To be blatantly honest, I don't work too much with Lucene in that. I'm a fan of Vespa, so that's my focus. And to get a good answer to that question, I'd refer to the great debate on Thursday, which will have experts both on Vespa and Lucene and on Elasticsearch to answer a lot of those different questions there.
Mm-hmm. Sounds good. Some people also asking about performance with comparison. I know, right? But I think the benchmarks that you mentioned would be like really the ultimate answer for those, right? So just like go to the website and people can find it, right?
Definitely. So again, we've added a pull request to add the performance of the ANN implementation Vespa to ANN benchmarks, but we don't really, provide the ANN code in Vespa as a library, as a standalone library. It's part of the bigger system. Still, we want to see how well it performs, but it's important to note that it's working in the context of a larger, search system, which does a lot of other stuff as well. So that needs to be taken into consideration too.
Yeah, sounds good. Another question actually from my side. So you mentioned this example with a budget, right? And me coming from e-commerce, I kind of like seen it like across the board, right? So do you see, because I mean, the easy solution would be saying like, hey, if budget is like out, right, you just like stop showing the things, right? But it also means that with a website like as a Yahoo, for instance, right, you can have like, like lots of impressions, right? And after suddenly they go like to zero. Is there like any ways that you can see that it's like still scalable and you can do it more dynamically, right? So you can, like a boost visibility a bit of like less, right? And kind of like a do of controlling algorithm like in a way, right? When there's like a lot of budget, right, you have visibility. If not, like it's kind of like becoming like less and less, but not drastically, right, from 1 to 0.
Yeah, so I guess there's different ways of handling that. You can kind of bake that into your kind of ranking function in a way, and that you have sort of kind of a graded decrease. And so on. You don't want to, suddenly come into the position where you only have ads to show, which all of them have used up their budgets and so on, of course. So we have different teams that work on this specifically, and those are just one of the kind of many applications that are in Vespa. And I really don't have full view into how they handle exactly this question, but they definitely have to solve that.
Sounds good. Thank you.